So today we are going to continue our discussions on the DRAM's data retention. So last lecture, we already briefly talked about the DRAM's data retention problem because we have the leakage in the DRAM cell. Therefore, the charge that you store there will not stay forever. So especially when you store data one, there will be many leakage paths to discharge the data one. We will talk about that later today. And also, when you store data zero, you may have some path to charge the storage node. But in general, storing data one will be more problematic than storing data zero. We'll talk about that why in today's lecture. And by JEDEC, the standard today is that every 64 milliseconds, you have to refresh the cell. And then the refresh is done by read operation, right? Not by write, by read, because you will have this read back operation. So when you read the cell, it will recover the data automatically. Then we have this distribution of the actual data retention time. Actually, only a fraction of the bits fail below this 64 millisecond requirement. But because of this tail bits, we still need to refresh to prevent the worst case. Of course, you may have some ECC error correction code, but we have to minimize the cost for the ECC. So here is an example how are we going to design the refresh cycles, or in terms of, let's say, the intervals. So here we are going to distribute the refresh evenly or uniformly across this 64 milliseconds, depending on the number of word lengths you may have in this bank. We are going to evenly distribute the read operation across the word lengths. So here we have this example, and we talked about that in the last lecture, how to calculate the percentage of the refresh. So here, when we do the refresh, we have to go to that particular row and read that row. So in the other 10 slots, we can do the normal random access. So that means giving the address from the controller, then you can go to the any row and then read that row or write that row. But at this particular time point, you have to go to this specific location and read that row. All right, so then let's continue today. So there are many leakage mechanisms to discharge the data when you store one here. So here we have some leakage mechanisms labeled by those passes here. So here, first one is this one PN junction, okay, leakage. Why? Because here we have the PN junction, right? So when you store data one here, this PN junction is reversely biased, right? This is a reverse bias. So here, the N node is VDD, right? And then your P well is grounded. So the PN junction is reversely biased. So if you recall the PN junction, right? So PN junction, if you recall your undergrad device physics, right? So you have this reverse, I reverse for the PN junction at negative voltage, right? So you have some current flow this way. That is this leakage path one. And then second one is the Guido. We are going to discuss that in the next slide. But I think in the previous lectures, we briefly talked about the Guido. This is gate-induced drain lowering current. We'll talk about that in the next slide in more details. But there's another mechanism to get this leakage current from the drain to the substrate. And then the number three is a regular off, or let's say subthreshold leakage current, right? So this is a transistor structure. Then, even though your gate voltage is zero or even negative, then you have the leakage path because VDD is applied to your drain. So you have this subthreshold current, right? In the IDVG curve, in the log IDVG, right? We reviewed that. So here, this is non-zero, right? So this is your I off. And of course, then the capacitor by itself may have some leakage path. If the capacitor is not perfect, you may have some leakage path through the capacitor. But this is normally not big deal. If you fabricate your capacitors well, with minimize the defect density, then the capacitor should be more like insulator. But it's possible, right? If you have some defect, then the charge may leak through the capacitor. So we have so many leakage paths for the charge to leak out. That's why the data you store here will decay. In terms of voltage, you will decay over time. So if you account for this decay, then the sense margin will be reduced. So here you look at this equation. So you will notice that this is a delta VBL, which is your sense margin. And here, the first term here is the same as the equation we showed you earlier. That's the regular nominal sense margin, right? It's 1 over 1 plus CBL divided by CSN, the storage node capacitor, and the half VDD. But due to the decay, because you will, if you have some retention time, T retention, then your storage node voltage, right? VDD, start with VDD, but will decay due to those leakage paths. So when you really read at this moment, you already decay by a certain amount, right? You have this delta. And then we have to account for this delta. So this is due to the decay of those leakage, right? So your sense margin will not start from the VDD. So you will start with certain reduced voltage. So here, to the first order, you can estimate what is this delta V, right? This is the leakage path in total. You have the total IL, the leakage current, times the time, that's the total charge unique over this period, and divided by the CS, the storage node capacitance. Then that's the voltage, right? Charge divided by the capacitance is the voltage. That's a reduced margin. So you will see the reduced sense margin because of the leakage here. So any questions here on this slide? Okay, so then let's talk about the GIDO, the number 2, in more details. So what is GIDO? Okay, gate-induced drain lowering current, So I mentioned before, so if you look at the IDVG curve of the transistor, so here we show some real data, right? So for the NMOS, normally we only show you the VGS positive. So you only see this part, and then we call this is your I off, right? The subthreshold leakage I off. But if you really sweep the voltage to the negative side for the NMOS, you see that the current actually increase with more negative bias. So this current may be even higher than your I off. This is the GIDO current, okay? Similarly for the PMOS, if you sweep to the positive side, then you will see this GIDO current. So in the device physics, this is what is happening. So when you apply basically the negative voltage, or let's say in general, your gate voltage smaller than the drain voltage, then if you think about the band diagram along this direction, okay? So this is the band diagram, okay, along this direction, right? From your MOS. So you have this overlap region, right, between the drain and the gate. So in this region, vertically, if you look at the band diagram, so the negative gate voltage, right, negative for NMOS, we are talking about NMOS, negative gate voltage is going to pull up the band. So that's why here this Fermi level of your metal is being pulled up. So then that will bend the band that like this, like your EC and EV. So if the voltage is very negative, then your band will be bent like this way. So to a certain point, your valence band here will be higher than the conduction band at the surface of the silicon. So here, at the surface of the silicon, because of this negative voltage of the gate, or let's say in general, you have a negative VGD, then at this point, the valence band is higher than conduction band at the edge or at the surface of the silicon. So you see here, the electrons in the valence band now will have a large probability to directly tunnel through the band gap, because you previously, for electron hole pair generation, right? You have to, let's say, excite the electrons thermally, right, from this valence band to the conduction band. So you need the thermal energy. But here then, since the band is now high, I mean the valence band potential is high, then you can directly tunnel through without the help from the thermal process. So this is called band-to-band tunneling, BT-BT, band-to-band, 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 okay, tunneling. So here then, of course, you have this tunneling, then you get free electrons here, and then you leave behind a hole in the conduction band. So basically, you create an electron hole pair. So here you create an electron hole pair. And then in this bias condition, electrons will go to the drain, and hole will go to the ground, which is a substrate. If you recall, this is similar like the heavy ion strike, right? We talked about that earlier in the SRAM. So basically, you create an electron hole pair, and because it's at the junction area, then those electron hole pair will split, and the electrons go to the drain because the drain is attached to positive potential, and then holes will go to the ground, which is the substrate. So then the current direction, right, is the same as the hole direction or opposite to the electron's direction. So then you have this current. This is ideal, the ideal. Okay. So why this Guido current matters? If you look at the bias condition in the DRAM retention mode, this is the typical bias you are going to apply, right? So here, for example, the word line is off in the retention mode, right? Our word line is, let's say, 0. But then the bit line is usually pre-charged to be half VDD, right? To make it ready or prepared for the next read operation. So bit 9 is half VDD, okay? And then your storage node here, for example, we store 1. Okay, you have VDD here. You look at this bias condition, and you will notice that we have the Guido condition. Why is that? So here the gate to the drain is negative. VGD is negative VDD, right? Then you have the Guido current, I Guido. And also here you have the regular I off or I sub threshold, because here VDD and this is half VDD, right? So then still the current will flow this way through the channel due to the sub threshold leakage. And then this PN junction, right? So we just talked about that. This is reverse PN junction, IPN junction. So you have all those contributions. So here, we say that the store 1 is more problematic than store 0. Why is that? So here, when you store 0, okay, then the I off will reverse, okay? If you store 0, then I off will go this way, right? I off, because now this is higher potential, then you store 0. So you will have current to charge up the storage node. Ideally should be 0, right? You have some current to charge up. But then the Guido effect, right, is negligible, right? Because here you have 0 and then gate is 0. So then you don't have too much difference. And also here for the PN junction, right? So you have 0 and 0, the PN junction, will not have too much contribution. Ideally should be 0. So you only have this I off to charge back. So that's why store 0 has less problem, right? Store 1, you have more problem here. So any questions? Okay, so then this is the retention mode in the static case. That means this cell will stay there in the retention mode, and there's no adjacent activity to the cell. But if you look at the dynamic situation, let's say even though this cell, let's say is in the retention mode, but you will have some activity on the adjacent cell, right? So for example, here on the left-hand side is a static retention mode. You mostly have the junction and Guido current and I-off currents. But then in the dynamic retention, that means, okay, so this cell is under retention mode, but you are writing the adjacent cell, okay, adjacent cell is being written. So here then you will have some disturbance from the cell to cell. So because an adjacent cell, you are going to, write, you are going to turn on the VLAN to the VPP. And then if they are close to each other, right, then you have this capacitive coupling from the VLAN to VLAN. So somehow this voltage could be transferred or coupled to this VLAN. So it's like this VLAN voltage will increase a little bit due to the capacitive coupling. So that will, increase, let's say this dash yellow current is a delta current that is induced by the delta V, which you have the disturbance from the VLAN. So then this vacant cells retention will be reduced because you have some activities ongoing for the neighboring cell. And then in the memory system security space, there is so-called row hammer effect. That means row hammer, it's like you are going to use a hammer to keep writing or reading from this VLAN. The purpose of that is to disturb the data on the adjacent VLANs as a attack, as one of the attack mechanism by the hackers to basically destroy your data. So if you keep writing the same row, then adjacent rows data will be, flipped somehow.
See that this capacitive coupling issue or disturbance happens at the dynamic mode. So in that case, to avoid this, we can go the static retention variant all the time, so that we don't have the wrong repeat.
In the static case?
Yeah, so why does that capacitive coupling not happen in the static
case?
Static
case means you do nothing here, right? So the coupling only happens when you have a transition, right? So if you do nothing, then yes, then there's no crosstalk, right? So the capacitor, only conduct the transient current. Only when you have the switching, the capacitor will work, okay? Even though here, yes, you have capacitor, but they keep the same potential, no operation, then nothing will happen, right?
The static retention, is it just I-off is not mentioned, but in dynamic it's mentioned?
So there should be I-off, but this I-off will be increased. So this slide I should say, or enhanced I-off, let's say. Because here it's like this gate voltage is higher, right? So if you think about the IDVG plot, log ID VG, in the static case, you are looking at here, this is really zero. But then in the dynamic case here, you are increasing this by a little bit delta V, right? Then you are looking at the I-off like here, right? So this is this I-off, and this is this I-off. But this is in log scale, right? Log scale means much larger. Okay. So then let's continue. So here, so this refresh is really a painful point for the DRAM system, right? Because as we do the refresh, the system is unavailable, right? We talked about that earlier. So when you do the refresh, you cannot do other things. So it's a waste or overhead to the system. So here, this is like a percentage of time spent on the refreshing, depending on the density of the DRAM chip. So typically it's like 10%, around 10%. And in this paper from the very famous Professor Onomutunu, who is now in ETH Zurich, and he predicted that as we further increase the capacity, then the refresh overhead will further increase. Today, the DRAM capacity is about like 32 or 16 gigabits. So, but I would say this was a prediction like 10 years ago. So actually what happened today is more like this. It's not that aggressive as he predicted at that time. The reason is that people came up with very many like mitigation schemes to prevent this overhead from the refresh. One strategy is to have less sub-bank. If you have a large bank, then yes, you are going to spend more on the refresh. But if you break, then that will help. Similarly, for the energy overhead, right? Typically like 15% in terms of the energy you spend on the refresh. So I would say the general trend is more like this today. Okay, so the refresh is not something you want, but you have to pay for that. All right, so then let's continue our discussions to the DRAM technology. Okay. So if you look at the DRAM cell capacitor, okay, there are actually two kinds of cell capacitor. Historically, the DRAM's 1T1C is different from today's mainstream. So this used to be the popular design where the capacitor is buried into the silicon substrate. So it's called trench capacitor cell. So here you have 1T, and the capacitor is really built deep into the silicon substrate. So that means this is the surface of the silicon, right? Then you build the capacitor this way, okay? This way. So you dig a deep trench, and then you cover the trench with a dielectric and fill in with the inner electrode and outer electrode. So this is in the silicon. And here are some images of this deep trench. So you have a transistor here, and then you build the capacitor really deep in the substrate, silicon substrate. So here it says that no production below 70 nanometer node. So this no longer exists in today's mainstream technology. And we'll talk about the reasons in the next few slides. But basically, with this kind of trench capacitor, you stay with the so-called 8F square layout rule, and we will show that in the next few slides as well. So it's very difficult to fill the deep trench with high K dielectric, and then there are many challenges in the scaling. So that's why the industry gave up this trench capacitor. So you may see some of those trench capacitor in some special processes today. For example, the embedded DRAM with logic process. And this was used by IBM and the Global Foundry, because IBM, partner with Global Foundry these days. But I don't know if today they still provide this process, but at least a few years ago, for IBM's power series processor, then this was still used. Okay, I don't know in 2024 if they still offer that, but at least 5 years ago, this was there. So we'll talk about the EDRAM later. So this process could be compatible with the logic. But in general, the DRAM is a separate fabrication. We talked about that before. DRAM manufacturer has a different fab, right? So then this standalone DRAM fabrication does not offer this embedded or the trench capacitor cell anymore.
that we cannot use it if it is having backside power delivery because you're in the silicon down.
Yeah, so this is in their like 14 nanometer process. So yeah, in their logic process, it's not in advanced logic, leading edge logic. So here are some like last generation of this 20 DRAM at 17 nanometer node. And at that time, you see this trench aspect ratio is already very high. Here, very important. What is aspect ratio? Okay, by definition, aspect ratio means the diameter of the trench, and then your height of the trench, height divided by the diameter is the aspect ratio. Okay, so that's why you have very tall, deep trench, very difficult for the fabrication. So then high-K dielectric was introduced at that time. So this is the last generation of the DRAM trench capacitor in the year 2005. Okay. And after that, the industry switched to this stacked capacitor cell. We talked about that before, right? So now the capacitor is fabricated after the transistor. In the previous process, then the trench is done first, and then you do the fabrication of the transistor and so on. So now the transistor is fabricated first, and then we stack this cylinder capacitor on top, okay, on the contact via of your drain, and this becomes a storage node, right? So this allows the transition to 6F square layout, and we're going to show that in the next few slides. So here, there will be some thermal budget issue. So basically, you already finished the transistor fabrication, and then the stacked cell cannot have very high temperature processing, like over 1,000 degrees Celsius, then that will melt whatever, metal underneath. So this will have some thermal budget for the capacitor fabrication. So here are some like images for the first few generations of the stacked capacitor. So here you have the transistor here and then stack the capacitor here. So here, this is a comparison between those two, right? So here, for example, for the stacked DRAM, then you can easily do the high-K dielectric deposition on the stacked trench, not trench, I mean stacked cylinder. And then it will allow you to scale to 6F square. So we will talk about that in the next few slides. So the only advantage that the trench capacitor is that the logic compatibility. So you can do the trench first and then finish your rest fabrication in the logic foundry. So that's why it's used for the EDRAM, embedded DRAM. All right, so then let's move on to talk about the layout. So here then array size, of course, then the length of the bit line, you can imagine that the length of the bit line is limited by the sense margin because the longer the bit line, the larger the capacitance, the CBL, then that will degrade your sense margin. So you need a sense margin like 200 millivolts to reliably read out the data. And then the word line length is limited by the RC charging of the word line because you have to maintain, or let's say achieve certain speed of the word line signal propagation through the word line. So you have to limit the word line length, right? When you turn on the word line from the edge, and then the pulse will take some time to reach to the end of the word line, then that will suffer from the RC delay. So here we have two array architectures in the DRAM, and one is called folded bitline architecture, and the other one is open bitline architecture. So the folded bitline architecture was compatible with this 8F square, the trench capacitor we talked about before. And today, this is a mainstream today. Today's mainstream is open bitline architecture with possibly 4F square, but today's the mainstream is 6. This is a mainstream today. And in the future, we are going to migrate to this 4F square, which is under the active research and development from the industry today. But on the market, okay, you will only see 6F square layouts. So let's look at how this is organized, okay. So here, if you think about each circle is one DRAM cell, this 1T1C, one cell. And then we have the word lambs and then the bit lambs, right? So the sense amp we talked about before, differential, right? Amplifier. Using the bitline true and bitline complementary T and C. So if you get the T and C from the same array, and you place the sense amp at the edge of the array, this is called the folded bitline architecture. So here, for example, those two adjacent bitlines will share this sense amp. And you can place the sense amp on two sides of the array. But here you will notice that at this location, this cross point, you cannot have the DRAM cell. Why is that? Any idea? So if you have DRAM cells here, you cannot have DRAM cell here. You cannot, right? Why is that? Because you turn on the word line, you're going to turn on the entire row. And if you have cell here, this cell will also charge or discharge, right? Then you do not have your reference, right? You do not have your reference. So you have to stagger this cell. So that means if you look at each cell's size, it's like you have, first of all, on the rows, this dimension is what, 2F, right? One wire, 2F, right? You have the wire and the spacing between the wire, you have 2F. So here on this side, horizontal side, you have two wires. Two wires, that means 4F, right? So you get 8F squared, right? Because here you lose some space here because you cannot place the DRAM cell there. Otherwise, you turn on the word line, then you do not have your reference. So the open bitline architecture we talked about before, we are going to, this is one array. We are going to share the sense amp with the other array. This is from the other array. So the sense amp will get one bitline from one array, another bitline from the other array, right? So we are going to activate one array at one time. So the other array can be used as a reference. Then we do not have this crosstalk problem. And then you can place here every cross point of the word line and bit line. You can have a cell, okay? Then that means theoretically speaking, each cell occupies this space. That is one wire and one wire, right? Each is like 2F and 2F. So you get 4F squared. That is the limit. But to allow bitman contact, we have to do 6f squared. I'll show that in the next slide. But theoretically speaking, with the open bitman architecture, you could allow 4f squared because each cell you only need one more than one bitman. That will be 2f by 2f. Okay. So then there's one advantage of this folded bitman architecture. That is, it has a common mode noise rejection. Why is that? Because here those two bitmans come from the same array, and they come from very, nearby those two word lengths. Oh, sorry, two bit lengths. So they may have similar common noise pattern. And then, the differential amplifier will, reject those common noise. So this is better in terms of the noise rejection. And then the open bitman architecture, because those two wires coming from two different array, they are far away from each other, so they do not share the common noise pattern. So this will have larger noise. That's the downside of the open bitman architecture. But it allows the better scaling, better area efficiency. So that's why the industry still choose open bitman architecture today. Okay. Any questions here? Okay, then let's show some real layouts. So here, this is just a summary. I will skip that. I already talked about the differences between the open versus the folded bitman architecture. And I said industry use 6f square cell below 14 nanometer node. Okay. And let's look at some real layouts. For the folded bitman, this is 8f square cell. And this is like the array schematic, right? So as I said, we have this staggered cell. The reason is that here at this location, we cannot have the DRAM cell, right? We cannot. So if you look at the real layout, this is how it look like, right? So here, the word line, word line means you are going to have a transistor across that. And then here you will have the capacitor on this side. This is top view, right? Layout is always top view. And then you have the bitman contact. This will be your storage node capacitor. And then this will be your bitman contact. And then you make this connection to the bitman. So here, this capacitor could be the trench capacitor. Of course, could be the stacked capacitor as well, depending on you are going to dig a hole here into the silicon for the trench, or you are going to stack a cylinder on top of the silicon here. But this space is reserved for your capacitor. So here we have this dash box, label one cell, 4F and 2F, right? 8F square. Any questions? You need to understand the layouts, okay? So this is the same requirement. If you recall SRAM, next year we ask you to understand the SRAM layouts. The same thing here apply to the DRAM. That means those will be on your homework or on your exam. So here, let's look at the comparison between, let's say, 8F square, 6F square, and the 4F square cell. We already showed you the 8F square cell. And then let's look at the 6F square, okay. 6F square, very important feature is that there's angle between the channel and your word line or the bit line. So here, this gray region, this is the active region where the channel direction is pointed towards. So if you look at, let's say, this one, so the channel is going to, let me maybe draw out, okay? Otherwise, it's hard to see this. So what you have here is, okay, the word line. This horizontal line is the word line. That is your gate, right? So your transistor should be across the gate. But the transistor direction, if you want to draw it, should be in this direction, okay? With some angle. You see this is tilted. And then this transistor gate and source and drain. So you know source and drain, one of that will be capacitor, right? One of them, let's say this side will be the capacitor. The other side will be the bit line contact. Right? The other side will be the bit line contact. So one for capacitor, one for bit line contact. Then here, if you have a bit line here, right? This is bit line, which is this shaded bit line. And then this side is your storage node, capacitor, right? So here then you look at this. So you will see that I should actually draw this way. Because this contact will be shared by another cell, okay? Actually, the other cell will also share this contact. So effectively, I should say, show this. You have 3F this way and 2F this way. Like what we show here in this dash box. That gives you 6F squared. That gives you 6F squared. So here, in the future, you have a question?
Lines are home, and then the reason you have two of them across the active areas is because the middle node is being shared. That's what we contact.
No. First of all, word line is metal. And so here, you mean we have two word lines?
Diagonal cylindrical active region. You have two word lines.
So there are two cells here. There are two cells. If you look at it's like two cells, okay? They're going to share the bit line. They share the same bit line, but you have two word lines. As I said, here you have two cells. They share the same bit line contact. You have to look at the layout carefully, okay? I will show you some more examples in the next few slides, so you will notice that the subtle features.
Maybe PLC for
Bit line contact. You need a contact wire, contact wire. So the future is 4F squared. So this requires the transistor will be vertical. I'll talk about that in the next few slides. But then this is the theoretical limit, 2F and 2F. The reason that today is 6F squared is because you have to make this bit line contact, okay? And then the key feature is that here the channel direction is tilted. This is very tight space, actually. If you look at the design rule, in your logic, let's say language, this violate all the logic design rule. It's mission impossible in a logic process to have this tight collection and spacing. So I will show you some real layouts. Okay. So this is the 6F square layout from Samsung. And here you will notice that, for example, here, let's say the horizontal word lengths and the vertical bit lengths, and then the channel direction. This is the access transistor direction. The channel direction, as I said, is tilted or twisted. So then, those two nodes, one of that will be contact, one of that will be capacitor, right? And this capacitor is standing up for the stacked capacitor. So that's the reason you have to make this like tilted, twisted channel. Why is that? If you make the channel direction like this, then yes, this one is a bit and contact. Then the other one will be your will be your capacitor. But your capacitor cannot stand up because on top of that you will conflict with this bit line. So you have to make an angle for this capacitor to stand up, right? That's why you have to make this tilted channel direction because your capacitor is standing up. If you have something prevent it's from standing up, then that's mission impossible, right? So that's why you see here is dash box, you have 3F and 2F. So any questions?
Where the sets have the current.
Sensum is at edge of the array. Yeah. To the bit line. And then you are going to share, right? So let's say you have this connect to your sense amp, and then you get another bit line from the other subarray, and then get to your sense amp, right? Okay. So here, this is another design. And you will notice that here let's say, here the channel is always like this, the same orientation. And in this particular design, I think the channel direction, yeah, it's still this direction, okay. But then I think in this case, they have some like a non-uniform in terms of the spacing between the word lengths, because there are some dummy isolating word length. You can look at the layout by yourself. But here the key concept we're going to discuss later is that this company proposes buried word line, which is important for the DRAM industry. This was proposed by this Kimonda company, which now already bankrupt. This was a company from maybe 2006 to 2010, based from Germany. And this company has a lot of actually innovations in the industry, and it has many patents, and many of them later was acquired by Micron, I believe. But this company, I want to mention that because this company, if you look at later lecture when we talk about the ferroelectrics, the ferro behavior was discovered by this company's researcher in the high K dielectric. When they make the DRAM capacitor in about 2006, they found out there are some ferro behavior in the DRAM capacitor. Of course, at that time, they didn't know and didn't publish till the company bankrupt. And then later, there was a research group, a research lab from Germany called NAM Lab. Then they took over, and then they publish and now become the mainstream in the ferroelectric tricks. So there was a history, I just want to say about this company, okay? So you can look at this layout by yourself and figure out the orientation of the channel and then the bitline contact and then the storage node capacitor, okay? And then here, there's another design proposed by Micron. So here you see that the bitline now is like twisted because the channel orientation actually flip like this. So, but then the good feature about this is that the activation, active area for the channel is continuous. So previously for those kind of design, maybe I should show this one. So then for the active region, they are disconnected. There's no unit isolation between those, okay? The gray region is where you dope source and drain, right, the active region for your transistor. So then in this particular design, then if you follow this, then this will be continuous. Then the downside is then the bitline is not straight, it's twisted. But anyway, on average, still you have the 6F square. So there are different flavors of the design, but I would say today's mainstream is this one, okay? This one, no matter which company.
Is this angle decided which?
The angle? That is a good question. So depending on the process, depending on the design rule by particular company, they may vary a little bit. And yeah, I don't know what is the limit on that, depending on the lithography, etching, blah blah. So it's a little bit different. Actually, we'll show that in the next few slides. The angle actually is changing over the generations. So I don't have that slide. Maybe maybe in this part, we'll show you some of the recent layouts. And also in your homework too, you will see that the angle. Okay, so any questions? So the DRAM layout, very special. And I just want you to pay attention to those few features. One is 6F square. Second is the active area or the channel direction is tilted. And this is to allow you to have the bitline contact and then the storage node capacitor in different spots. Therefore, the storage capacitor could stand up. That's a key. Okay, so then let's talk about the scaling challenges. So if you look at the DRAM design spec, okay, the first thing is that we have to maintain this sense margin, right? This delta VBL, and given by this equation, the first term is the nominal behavior. If you consider the leakage, then you have the reduced margin by this amount. So you see that those parameters, right? So let's say if you maintain this larger than 200 millivolts for practical design, then your CBL versus CSN needs to be maintained. And then the cell leakage current needs to be minimized. And then on top of that, here, why do we need 200 millivolts? Because this needs to compensate for any process variation and also thermal noise to deterministically read out the data, right? Because the transistor mismatch of this sense amp, you may have some built-in bias that is called offset. So even though you have the, let's say, this one is larger than this by 10 millivolts, but due to this bias, it may detect wrong because this mismatch of those differential pair transistor like VTH mismatch, then you have some built-in bias that is offset. And then in terms of speed, right? So then what matters is this on-state current of this access transistor and also parasitic RC along the word line and bit line. So those are the key parameters. So let's talk about the cell capacitance first. So we want to maintain the cell capacitance with the scaling. So here, this is a brief history of the cell capacitor fabrication. So in the early days, at the very beginning of this industry, it's SIS capacitor. You know, capacitor is two plates and the dielectric in between, right? So in the very early days, the two plates are silicon, like your polysilicon, doped silicon stuff. And then the insulator in between, so it's SIS. And then they change it to MIS, right? MIS, you change one of that, become metal. And then eventually we become MIM. This is the ideal capacitor, right? You want the metal. And especially then we pay attention to the I, right? So why is that? So here the capacitance, you know, this simple formula from your high school physics, right? Capacitance is epsilon of this material, of this insulator, times the area and divided by the thickness, right? Then the area and then the epsilon of this material. So here to increase the capacitance, first of all, let's say by scaling, what will happen? So actually, this is a good question. By scaling, so first of all, what is A? Let me ask the question. Our capacitor is always the cylinder capacitor, right? It's not this plate. So you have to think about the cylinder, right? So let's say on average, you have the diameter D. You have the height H, right? And then we define this aspect ratio is H over D. Then what is A? Yeah, so here is like pi D, right? The perimeter is pi D, right? Times H, right? That's the surface area. Is that true? Okay. So with the scaling, we are scaling what? D, right? D is like your F, right? So with the scaling, we are going to have smaller D. If you do nothing, then the C storage node will decrease. That's not good for your sense margin, right? So you have different ways to increase that. One is to, of course, change the dielectric constant, epsilon, the permittivity, from silicon dioxide to this ONO, silicon, not silicon, I mean oxide nitride, like SiO2 become SiON. You have some nitrogen. And then you have to switch to the high K material, like the gate we talked about before. Like for the logic transistor, the gate stack, we change it to a high K. Similarly, we change to a high K. And then I think today, industry, what they use is zirconium oxide. Or maybe that's some secret, but the majority of that material should be zirconium oxide. Maybe different companies have different dopant a little bit. And this material has the dielectric constant roughly speaking 40. Yeah. Compared to the silicon dioxide, it's about 4. So you see the epsilon increased by 10 times. And then the height become higher and higher because you have to compensate for the shrink of the D. And the thickness does not really change too much because you have to maintain the leakage through this, right, the tunneling. So here, the capacitance typically in the old generations is about 25 femtofarad per DRAM cell capacitor. This is from 1980s. And then even for today, it's about 10 femto. Okay. For today, maybe 5 to 10. It shrink a little bit, but it does not exponentially decrease, right? If you think about the dimensions scaling, right? From the 1980s to today, 40 years, we showed you the scaling trend before. The dimensions reduced by more than 1,000 times already. But then the capacitance only changed by 2 or 3 times. So we have to maintain this CSN. Because you cannot allow your sense margin to decrease by 1,000 times, right? So this is the key challenge in the DRAM cell capacitor fabrication. So I showed you some like images. So previously you have this MIS structure, and then one of the S is this polysilicon, and then now we become this MIM. For example, M could be nitride. Nitride is a kind of metal, as I mentioned before. So tinitride or tantalum nitride is conductive. It's like metal. Okay. And then the I could be this aluminum oxide, but today we switch to the zirconium oxide. So here we summarize, right? So the bit and capacitance change very little over the generations, as I said. So the bit length gets shorter, but all dimensions get smaller as well, right? So then your bit length gets shorter, yes, but the spacing between bit lengths also scale. That means the CBL, right, which is wire-to-wire coupling capacitance increase, right? So you think about the bit length. Between bit length, you have the wires. You scale the F. This capacitance actually increase. Of course, then you scale this length as well, right? You keep the same number of cells, let's say 1,000 cell, and then you shrink this dimension, you shrink this dimension, then they cancel each other. The key is that CBL does not really scale. That means your CSN should not scale. That's why still, I said here, today, you still need to maintain 5 to 10 femtofarad. You cannot allow the CSN to scale because your CBL does not scale. Because the margin, right, depends on this CB over CS. Yeah, as I said earlier, so the DRAM subarray size typically more than 512 to 1,000 along the bit line. Yeah, on that order. On the word line side, you can have more, even more, but on the bit line side, typically 512 to 1,000. Yeah, this is larger than SRAM. SRAM is like 128, 256. Yeah.
In the CSN, mainly we are increasing the height.
Yeah, so we are going to show that in the next few slides, how to maintain that. So here, let me show you this concept EOT. I think I mentioned this before for the logic gate stack when we talk about the high K metal gates. So the same thing applied to here, the equivalent oxide thickness EOT. That means if you treat the high K material the same way as silicon dioxide, then effectively you are looking at thinner EOT. If you treat your high K the same as silicon dioxide, then that is the effective thickness if you are using the silicon oxide. So this is another metric to evaluate how thin or how high the capacitance is. So basically you want smaller EOT. That means you are That means you are keeping the same, of course, in the reality, you are not using the silicon dioxide. But here you are assuming if you stay with silicon dioxide, then you keep shrinking the silicon dioxide thickness, right? This is the EOT. You keep shrinking this one with the high K. Then what is the thickness? Assuming you are using the silicon dioxide to get the equivalent capacitance as you are using the high K, okay? So today's EOT typically is like 3 to 4, 4 to 5 angstrom. Angstrom, okay, here the unit is angstrom. Below 1 nanometer. Of course, this is equivalent. Physically, it's larger because you have high K. So we will talk about that, the transition to the ultra high K and then the pinner capacitor in the next few slides. So the high K. So here, this is a survey of the different materials. This also applies to the logic transistor, the gate stack. So one industry pick somewhere here, like hafnium zirconium oxide. This is because there's a trade-off between the K value, which is dielectric constant. It's around like 20 to 40 in this space versus the band gap, okay? Band gap is around like 6 electron volts. So silicon dioxide here is on this end. So the K is only 4, but you have very high band gap, like 9 eV. So here we, of course, want higher K, but then the trade-off is that you have lower band gap. Then that will cause a problem because this capacitor, right, you have the direct tunneling. Direct tunneling. If you look at the band diagram, right, what matters is the band gap of this insulator. If this band gap is small compared to your, silicon, or let's say your metal, then they can easily tunnel through. That gives you the leakage current. I said leakage current through the cap itself is negligible, right? But if you choose some material like here, then you have very, shallow band gap. Then this leakage current could be very significant because the leakage current, this tunneling current exponentially depend on the band gap of the material. So even though you have higher C, you also have higher leakage current here. So that's not good. So that's why here we choose somewhere in the middle, okay? That's why those two materials stand out. And that's why later I said, when people dope or mix hafnium zirconium oxide together, they discover there's ferro behavior. And the ferro behavior come from the DRAM guys when they do the research on the high K material. We'll talk about that later when we talk about the ferroelectrics. Okay, so the capacitor shape, right? Previously, it's more like the cylinder type. What is that? Is that the storage node actually stand up like this? You have the drain contact here, right? Contact via to your drain of the transistor. And then you're going to have the metal, like a U-shape metal first. And then you fill in the sidewall by this dielectric. By the way, the fabrication is all ALD, okay? Atomic layer deposition. Therefore, you can cover this very high aspect ratio like hole. And then you deposit the plate metal. Then you get the capacitor, okay? So if you look at the critical dimensions here, you need to have, this is the total dimension of this cylinder. You need to have the middle like electrode plate dimension, and then you have twice thickness of this capacitor. And then you need to have this twice of this SN electrode thickness. So the recent move for the past few years is to change from the cylinder to this called pillar type. So here the storage node, when you connect to the, let's say the transistor underneath, so you are going to build a pillar like this one, and then you cover the dielectric this way, and then you fill in your plate on top of that. So in this case, then you are going to save some of the space here. You do not have the storage node thickness. So this is another structural change in the recent years.
How is it supporting scaling?
Because you get rid of, you look at this, you get rid of this thickness of the storage node. Right. So here we mentioned that the scaling really means stacking higher and higher capacitor, right? If you recall here this equation, right? So as you scale D, you are going to make H higher. So this is what's happening. Actually, your AR aspect ratio is H divided by D, right? You are making D smaller, then you are actually increasing the H. So aspect ratio actually will increase further, even more, right? Let's say you decrease D by 2 times. Let me say, D become 50% of D, and H become twice of the H. Then aspect ratio actually increased by 4 times, right? Because you want to maintain the capacitance, C, right? Epsilon times pi dH divided by A, divided by thickness, right? If you do not change other parameter, you decrease this by 2, increase this by 2, then your aspect ratio increase by 4, right? So that means this, relatively speaking, this is become very, very tall and high. So today's pinner cap aspect ratio approaching 100, approaching 100. So that means here the dimensions today, for example, 12 nanometer or 13 nanometer here, right? Then here you have like 12 nanometer. You have 100 aspect ratio. This is like 1.2 micrometer of the capacitor, right? It's very, very tall. Any questions here? The aspect ratio. So that will give you some troubles, right? The mechanical stability is a concern, as it's like you are building the skyscraper, right? So these high buildings, then it may fall down. So that's why here it introduced, in the fabrication, it introduced some support layer. I don't know what is that exactly, but basically when you build this very high standing pillar, you need to have something in between to mechanically support, otherwise they may fall down or, have short between the adjacent standing pillar. So this mechanical support was introduced in the 20 nanometer DRAM. So here, this is a summary, right? So here, as I said, so moving beyond the like 20 nanometer nodes, AR ratio 80 or approaching 100 today. And then dielectric is some kind of zirconium oxide with some secret recipes, we don't know. But the majority should be zirconium oxide. And then you want to maintain the CS about about 5 femtofarad. And then the leakage across this cap should be below this density, less than 1 E minus 7 ampere per centimeter square. That's the current density for the leakage. So that's the requirement for the capacitor. So I just want to give you a sense what kind of capacitance value it is, and what kind of geometry, like factor, like this AR ratio. So those are the key features you need to understand for today's DRAM cap. Bit-length capacitance, so should be on the same order, like femtofarad, femto. Yeah. Okay, so I think that's for today. We'll stop here.